Hi everyone. In this lesson we're going to look at modular arithmetic. So modular arithmetic has a wide variety of applications. If you are considering studying cryptography, or if you're into computer science or chemistry, even music and finances and economics, modular arithmetic comes in handy. So when we're talking about modular arithmetic, or what we call a modulo M system, it consists of a set of M elements, 0 all the way up to whatever that M equals. So if we're looking at, like, say, modulo 7 system, it would consist of the numbers 0 through 6. And you might remember this when we were looking at different bases back in chapter 4. So some of this will be familiar to you, especially when you're looking at the table. So the system contains those elements and a binary operation. So two things I want to discuss with you. When we say the word system, we're talking about a mathematical system. And remember, a mathematical system just consists of a set of elements and at least one binary operation. And when we say binary operation, what we mean is that, adding or multiplying, subtracting or dividing, they're operations, right? Binary means 2. So it's when you can do one of those operations on 2 elements and it results in a single element. So for instance, you can take the numbers 2 and 3, that's 2 elements, and if you add them, you get 1 element, which would be the number 5. Okay, so a modulo system is a mathematical system, and it consists of M elements and a binary operation. Okay, so let's start out with this question. If today is Sunday, what day of the week will it be in 23 days? So I could sit here and, write out all the days of the calendar and count to 23, but there's a much quicker way of figuring that out. So since we're dealing with days of the week, I know that there's 7 days of the week, and then it repeats itself. So if I take the number 7 and I divide that into 23, we know that the most 7 will go into 23 is 3 times, right? 3 times 7 is 20, and if I subtract them, I get 3. So it's 3, remainder 3. So what this really represents is it's 3 weeks plus 2 days. So I know that if I'm dealing with today being Sunday, what day of the week will it be in 23 days? I only care about the days part. I don't care about the weeks part. So starting with Sunday, I know 2 days later, it's going to be Tuesday. So therefore, Tuesday would be the day of the week that 23 days later would fall on. What we just did there was what's called a modulo. And a modulo, in this case, would be modulo 7 system. And it can kind of be helpful to think about a table, which, again, if you'll remember, these look very similar to base tables that we had in chapter 4. So when we're dealing with the number 7, when you divide by the number 7, at most, you can get a remainder of 6, right? So you'll have either a remainder of 0 all the way to a remainder 6. Okay, so this is what a modulo 7 table would look like. As you can see here in that first row and in the first column, it's just the number 0 through 6, because if you add 0 to any of these numbers or these numbers, you're just going to get those numbers, right? And 7 goes into each of these numbers 0 times with those remaining. But when you get to this right here, right, if I add 1 plus 6, that gives me 7. 7 goes into itself with no remainder. So that's what that 0 represents. Okay, if I add 2 plus 6, I get 8. Well, 7 goes into 8 one time with a remainder of 1. 3 plus 6 is 9, and 7 goes into 9 one time with a remainder of 2. So these are your remainders, if you think of it like that. When we get to, any of the numbers inside this table, okay, they act as remainders when you're dividing by 7. Okay, and those remainders are important. So let's say we want to calculate 4 plus 6 and modulo 7. What would be the sum? So I know that 4 plus 6 is equal to 10, right? But if you look in the table, you're not going to see the number 10 because when you're dealing with a set of 7, when it's a system 7, you should only be dealing with 7 elements, which would be 0 through 6, because when you divide by 7, you're never going to have a remainder greater than 6. It's either going to be 0, 1, 2, 3, 4, 5, or 6. So what I need to do is I can look at the table and go, okay, 4 plus 6, right? It's giving me 3. How are they getting that? Because if it's a system 7, I can just take 7 and divide that into 10. And we know that when we divide 7 into 10, we get a remainder of 3. So that's what that 3 represents. So what we would say, though, is that 10 is congruent. And if you think of like geometry, congruent basically means equal. It's congruent to 3 in modulo 7. Okay, and that's an important concept in modular arithmetic. So A is congruent to B modulo M, and it's written like this: if A and B have the same remainder when divided by M. Okay, so we would express the relationship like that. And how would we know this? If we divided 10 by 7, or if we divided 3 by 7, we would get a remainder of 3 both times, right? So we already showed 7 goes into 10 one time with the remainder of 3. 7 also goes into 3 0 times with the remainder of 3. So we would say that both of those numbers are congruent in that modulo. In any modular system, we can develop a modulo class by placing all of the numbers with the same remainder in the appropriate modulo class. So for example, all of the numbers in this first column here, if you divide 7 into each of them, right, they're all divisible by 7, so they have a remainder of 0. All of these numbers have a remainder of 1 when you divide by 7. All of these numbers have a remainder of 2 when you divide by 7, and so on, okay? Every number is congruent to a number from 0 to 6 in modulo 7. So for instance, the number 24 is congruent to 3 as long as it's mod 7, okay? 26 is congruent to 5 in mod 7, okay? Because they're in the same modulo class. So each of these columns here is a class. So that's what we're talking about when we say classes. Okay. The solution to a problem in modular arithmetic, if it exists, because it won't always, is going to be a number from 0 through m minus 1, where m is the modulus. So remember, when we're dealing with modulo 7, we will only have digits 0 through 7 minus 1, or 0 through 6. Okay. Let's look at some examples. So here we need to determine which number, 0 through 6, the following numbers are equivalent to in modulo 7, okay? So you could refer to the table if you wanted to, or you can divide by 7 and look at the remainder. So 7 goes into 44, we know 6 times, and there's a remainder of 2. Okay, so that tells me that 44 is congruent to 2 when it's modulo 7. And if you think about it, if you look at the column, 44 would be in class 2, right? Because you would have 30 plus 7, which is 37, plus another 7, which is 44. Okay, or you could come down here and do 28 plus 7 is 35, 35 plus 7 is 42. So 42, 43, 44. And as you can see, it's under class 2. So 44 is congruent to 2 mod 7. Okay, and the same we would do for 91 and 165, right? So as long as this number is not a number from 0 to 6, we need to, calculate or use the table. So here I'm going to go 91 divided by 7, which actually goes in an even number of times, 14, remainder 0. So that means that 91 is congruent to 0 modulo 7. Okay, 165 is not a number from 0 to 6, so I'm going to just divide 7 into 165. This time I know 7 can go into 16 two times. 7 times 2 is 14, and when I subtract those, I get 25. 7 goes into 25 at most 3 times, and there's a remainder of 4. So that tells me that 165 is congruent to 4 modulo 7. Okay, we can do the same thing when we're adding. This time we're going to add in modulo 9, switch it up a little bit. And we don't have a table to refer to, but you're welcome to make one. So if you were making a table for modulo 9, it would go from 0 to 8 along the top and then 0 to 8 along the column. Okay, remember you should only have the digits 0 through 8 in the table. As you can see here for modulo 7, you can only find the digits 0 through 6. All right, but it's easy enough just to divide. So 7 plus 8 is, here we're looking for the numbers 0 to 8, okay? And 7 plus 8 does not give us a number between 0 and 8. It gives us 15, right? So I'm going to take 9 into 15, and I know that it goes in one time with the remainder of 6. 1 times 9 is 9, plus 6 is 15. So that just tells me that 7 plus 8 is congruent to 6 modulo 9. Now when I subtract 8 minus 5, that gives me the number 3. And 3 is between 0 and 8, so I'm done. 3 is congruent to 8 minus 5 is congruent to 3 modulo 9. 7 times 5 is 35. That's certainly not between 0 and 8. So I'm going to divide 9 into 35, and we know that 4 is too high. 3 times 9 gives me 27, and when I subtract those, I get 8, which is the highest remainder you can get. So I know 7 times 5 is congruent to 8 modulo 9. And you all can try the check your understanding 1 to 3 there. So feel free to pause the video at this point and kind of reflect on what you just learned. And if you need to go back and revisit some things, that's okay too. So here we have some problem solving. We want to determine the positive number replacement less than the modulus, right, for the question mark that makes the statement true. So think of the question mark as your unknown, or, we would know that as x, okay? So what we need to do is we need to replace that question mark with a positive number, in this case, less than 7, right? So replace with a positive number less than 7, and so on. Here we would replace with a positive number less than 5, and here we would also replace with a positive number less than 5. Okay, so 3 minus 5 equals question mark mod 7. So what I need to do is I need to think about, like, how could I work backwards to getting my answer, okay? So you can do trial and error with this, or what you can do is you can take this number here, 7, and I'm going to add that to the number 3. Okay, so I'm going to have 3 plus 7, and then subtract 5 equals, or is congruent to, question mark, mod 7. Okay, so 10, 3 plus 7 is 10. 10 minus 5, we know is 5. And 5, we know is congruent to itself, okay? Because that's a number that's positive that's also less than 7. So the question mark is just equal to 5. Okay, and you can try that. So we know that if this is 5 here, 3 minus 5 gives us negative 2. And we know 7 can't go into negative 2, right? So think of 7 basically into nothing. There would be a remainder of 5 there. Okay, number 2, we're going to do the same thing. This time the question mark's in a different place. So we just need to think of like, okay, what number minus 4 would equal 3? Okay, and you can do that in your head. So if I add 3 and 4, I get 7, right? The problem is that 7 is greater than 5. Okay, I need numbers that are less than 5. So I'm going to divide 5 into 7. And you know that 5 goes into 7 one time with the remainder of 2. So in place of that 7, I'm going to put 2. Okay, therefore 2 minus 4 would be congruent to 3 mod 5. So the question mark would have to be, in this case, 2. Now when we're multiplying, it's kind of easier to do trial and error. So if you start with the number 0 and go all the way up to 4, right, because we need a positive number less than 5, if I do 2 times 0, we know that's just equal to 0. If I do 2 times 1, we know that's just going to equal 2. Okay, if I do 2 times 3, I get 6. 6 is more than 5. So I need to divide 5 into 6, okay? Sorry, I'm doing 2 times 2 first. So 2 times 2 is 4, and that's okay. It's here, 2 times 3. That turns into 1, because 5 goes into 6 one time, remainder 1. Okay, now keep in mind we're trying to get 3. So now if you do 2 times 4, you get 8. And 8 is too big. It has to only be the digits 0 through 4. So 5 goes into 8 one time with the remainder of 3. So you just found your answer. Okay, that's the one that works. So the question mark then would have to be 4. And I'll let you try the other ones on your own. Number 4 is a practice problem. It's a practical application that you can try. And if you have any questions, you can feel free to ask me in class. Have a great day, everyone.